Hello everyone, welcome to Structural Insights. Today we will see IS 14593 1998. This code is for design and construction of board cast in situ piles founded on rocks. So how this code is different than IS 2911? This 2911 we have already covered in our last videos. 2911 is mostly for the piles founded on clays or in sandy soils. But if you are encountering rocks means weathered rock, fractured rocks, good rocks, maybe sound rocks. So all these rocks are given in the categories of the rocks based on the QC properties, unconfined compressive strength properties, and SPTN values are given in IS 2911 Part 1 Section 2. There is a table by Cole and Stroud. This table gives the properties of the rocks, fractured rocks, and their classification. Based on that classification and field test values, N values, and lab test values, the QC values, we can classify the rocks, and based on that classification we can evaluate the pile structural capacity or the rock capacities uh, for a given load. So first of all, we must understand that this code is applicable only to the piles of diameter equal to or less than 1500 mm. Okay, for pile diameters more than 1500 mm, this code is not to be used. Also, this code does not cover the well foundations. Okay, so these are the now these are the references, and we must keep in mind that these are the older references, like 1978, 456. The latest reference is 2000. Similarly, 2911. Latest reference is 2010. These are the old references. Okay, so this is also old. 4651 is revised in 2021, 23, I guess. Some revisions are there after this one, so that we can refer. Now let's there are some other references given. So 4651 is basically for the marine construction pile. If you are constructing in marine, then you better refer IS 4651. So this gives the load combinations, various loads that are to be considered in marine environment. These are given in IS 4651. And now what is a rock socket? These are the references. Then we have this rock socket. What is this rock socket? So rock socket is nothing but when you are making a pile foundation in a soil where you are encountering rock at the bottom, so how much your pile will go inside the rock is known as LS. This LS is nothing but rock socket. Suppose I have this soil top. Okay, I have this pile and this is the rock. This is rock, this is soil, and your pile is going this much inside. This is called LS. This is called rock socket. Necessary information. We should know IS 2911 Part 1 Section 2. We already know that. We have covered this thing. Geotechnical investigation report IS 1892. IS 1892 will give you that for a given project site, for the importance of the building, for a given area, how much borings are required and how much depth you should go for a given importance of building. These things are given in IS 1892. This we can cover sometime later. The rock profile contours, like you should know that if your rock is weathered, then you should know that what are the discontinuities profile, whether they are vertical, they are horizontal, they are inclined, what is the inclination angle. This data you must have. This we get generally by taking successive board logs and then understanding that how a given discontinuity is getting reflected in the next board log. So this will give you overall profile of the cracks and discontinuities. This type of study is mostly done in very important structures. This data may be available, may not be available. It depends upon how much borings you have done. So this data is required. Then information of the rock below the anticipated level of pile tip. So say you are expecting that your piles will go up to say 25 meters below the ground based on your preliminary geotechnical information. So you know that this is a soil type and this is a rock type, and for my given rock condition, I require to piles to go at least 25 meters down, and beyond 25 meters I want say at least 5 more meters of geotechnical information. Like I should have a board log data which is extending up to at least 30 meters, not less than 5 meters. 25 plus 5. If it is going 30 meters, your pile length is 30 meters, then 30 plus 5, 35. So this you must ensure. Then In case of bridge on pile foundation data on high flood, so if you are constructing a bridge, then you should know high flood level so that you can keep your deck level above. So keeping your deck level above these levels, high flood levels, then your pile length will increase. If your pile length will increase, then structural capacity will reduce for a given diameter. So these things are to be considered. Then results on chemical test. This chemical test means the chlorides and sulfate contents of the soil will determine the exposure conditions. Exposure conditions based on these parameters is given in IS 456. So you can go to IS 456 and see what is the content of chlorides and sulfates in the soil and in groundwater. Based on that, we will arrive at a given minimum grade of concrete, minimum water cement ratio, minimum cement content, which is given in IS 456. So we should know what is the chemical profile of the soil and the water, and that will also decide if we need any kind of silica fumes or any kind of fly ash for increasing the impervious nature of the concrete. So these things will be decided based on the chemical properties of the soil and the groundwater. Equipment and accessories. Boring. So we know that the boring is required to make board cast in situ piles. So boring can be done with two methods. This is baler and chisel, and second one is the rotary method. The baler and chisel method is like baler is like hammering. You are hammering it, breaking it, and through baler. Chisel is like a hammer, and baler is like collecting the broken pieces. So chisel and baler. So if you have a board log, so you have this soil, so you are chiseling it. Chisel is like you are hammering it, dropping it from certain height, then you have some broken pieces, so you take out these broken pieces through baler. So this is called chisel and baler method. And then we have a one more method is there, which is called as rotary method. In rotary method is like a there is a rotating blade which is rotating and advancing in the downward direction, and it is being operated by a machine which has a given torque and rotation capacity. For it has a given energy, and based on that energy, and if your torque is increased, then number of rotations will decrease. It's something like that. So it is a continuous kind of operation. And baler and chisel is like you're hammering and collecting, in this rotary is like you're continuously operating, and it is penetrating the rock. So cutting tool. Drilling mud is nothing but bentonite slurry, which is a thixotropic material. It is used to bentonite. It is used to stabilize the borehole walls for weak soils. Cleaning. So when you are drilling and cutting, you need to clean the scrap, right? Broken pieces, you have to take it out. So you can clean with the there are many tools that are used to be cleaning. Some are mentioned here. Rope operated grabbing, Cali mounted hydraulically operated grab. Grab means grab. Actually, whatever it is, like English says like this. So you're grabbing something. So this is called grab. Liner. So what happens is like liners are mostly required in marine environment, independent of any other factor, because they act as a shuttering for the piles. For ground where there's no marine environment, liners may be required when your soil is contaminated or groundwater is contaminated. In that condition, we don't want that our fresh concrete or the you can say green concrete to directly come in contact with the groundwater or the soil which is chemically contaminated or some other reason, because green concrete is more susceptible to getting damaged by this groundwater conditions if they are aggressive. If it is set, the gel formation in the pores has taken place, then there is no problem. We can later remove the liners, and we can keep the concrete exposed to this thing, because we have designed our concrete for that kind of exposure. Then design consideration. So what should we keep in consideration while designing the piles in rocks? So our structure should not fail, and our rock should also not fail. You should have enough structural capacity, like pile should be able to take the structural loads, and when we are transferring these structural loads to the rock, your rock should not fail. That's all is given in this paragraph. So let's go ahead. So we have to also see how many types of loads we should check before arriving at the capacity, like lateral load, vertical load, seismic loads, wind loads. All the loads should be applied in the given load combinations. Load combinations can be taken from IS 456 2000. If it is a dynamic analysis, it can be taken from IS 1893. and so these things are you can consider. And then after proper analysis, you get certain combination of vertical force, lateral loads and moments. These vertical force, lateral loads and moments you apply on the pile top, and then we design our piles, and we check whether the capacity of the pile and the rock is adequate or not. If it is not, then we modify our design. So loading on the piles. So loading in the piles can be axial. Axial means compression or tension. Lateral loads and moments. So these are the horizontal forces and moments. The various load combinations of dead load, live load, and wind load, earthquake loads, and uplift load to be considered should satisfy the requirement. So this we have already discussed. The overburdened soil may exert negative skin friction. If there is a negative skin friction in the soil, soil is very loose, then what happens is the soil will try to compress the pile. So your capacity, the vertical load bearing capacity will reduce. Suppose you have a total pile capacity of 1000 kilonewtons, and your negative skin friction is applying some load of 250 kilonewtons. So your net usable capacity will be 1000 minus 250. That is 750 kilonewton only can be accommodated from the structure. That is the purpose of including this paragraph. On the properties of the rock in which it is embedded and socketed. Axial load from a pile is normally transmitted to the rock through adhesion at the interface of the pile and rock and end bearing at the pile tip. Okay, so this is saying that whatever axial load we are transferring to the pile, it is going into the socketed length. So this is this is a difference. There is a difference in this capacity evaluation and the one that we did in 2911. In 2911 we are taking the skin friction from the upper layers, and then we are evaluating the pile capacity, structural capacity. Here what is happening is whatever your length you are embedding in the rock socket, LS, that LS length is only considered for the skin friction evaluation, for uplift capacity, for vertical downward capacity, and if it is a vertical bearing capacity, then we take end bearing resistance also, but in uplift we ignore that thing. Okay. A single pile is normally designed to carry load along its axis. The horizontal load on a vertical pile, IS 2911 part 1 section 2, we have seen the horizontal subgrade reaction. So from there we can evaluate this lateral load capacity of the pile, and we can provide the required reinforcement. Okay. The permissible load carrying capacity of the pile may be estimated using the proposed method. However, it should not be confirmed by an initial load test on trial pile. So this is saying that you can evaluate the pile load carrying capacity using the formulas given in this code, but you should not say that these are the final formula and you can start using, you start constructing your piles. You should perform one initial load test. Initial load test is actually a site test, in field, in situ test. So there you construct a pile and then you load it for vertical load, for lateral load, for uplift load, and for a given load. If your load capacity is a safe load capacity is 1000 kilonewton, so for say 2.5 times the 1000 kilonewtons, you apply the load and you measure the settlements, you measure the lateral deflections, and then you decide the pile capacity. So that is an actual load capacity of your pile when you are performing initial load test. So IS 2911 gives the exact number of piles on which you must perform initial load test or routine test for a given site. These things are given there. These things are not covered here, but here something is covered, like for initial load test, how much load you should apply, what are the deflections and settlements you should observe, and based on those deflection settlements, how to arrive at the pile capacities. These things are given here, so that we'll see slightly later. So this is the paragraph we have covered. Now let's move ahead. The settlement of the pile obtained at the safe load from the load test results on a single pile shall not be directly used in forecasting the settlement of a structure unless experienced from similar foundation on its settlement behavior is available. So what they are saying is, when you are evaluating the pile settlement analysis from the load test on a single pile. So suppose you are from initial load test, you are arriving at a pile capacity of say some 1000 kilonewton for settlement of 12 mm. So this, by doing this, you cannot say that your whole pile foundation with n number of piles will also settle by 12 mm for n into 1000 kilonewton. So that thing is to be, you cannot commit that, because when one pile interacts with another pile in the vicinity, then the net pile capacity is generally reduced. So what happens is, like, we have to be very cautious while deciding the total capacity of the pile cap when n number of piles are there, and this capacity is mostly less than the individual pile capacities added together. The average settlement may be assessed on the basis of properties of the soil, subsoil rock, loading details of the structure as a whole using the principles of rock mechanics, or as given in 6.6. We'll see in 6.6. So estimation of load carrying capacities. So compression. So load carrying capacities can be estimated using these four methods based on uniaxial compressive strength, and structural capacity of the pile. We can also use pressure meter test, limit pressure of the rock, and shear strength of the rock. So mostly what we have seen is the A and D are more important. So we'll discuss these two here. So so now this notes. Number one, first note is saying that for suggested minimum length of the socket can be based on the rock type. If it is sound and relatively homogeneous rock, we can use 1D to 2D of the socket length. Socket length is nothing but LS, that we have already seen above. LS is the length of the pile that is going inside the rocks as a socket. So it can be 1 or 2D. D is the diameter of the pile. Here it is written. Okay, and moderately weathered rock closely jointed including schist and slate. So if it is moderately weathered rock, then 2D to 3D, and if it is soft rock, then 3D to 4D. So this is given here. Based on uniaxial compressive strength, where the rock is sound, the strength of the foundation rock is generally much in excess of the design requirement, provided the walls of the discrepancies are closely and they are favorably oriented. Refer to figure 1 of IS 120. So IS 12070 gives for a given fractured rock or weathered rock profile, what is the alignment of joint continuities, whether it is a vertical joint, horizontal joint, vertically inclined, horizontally inclined. So what is the type of joint, what is its orientation, based on that the capacity has to be considered accordingly. So for that we have to refer IS 12070. Meanwhile, let's come at the capacity, how to evaluate this. So this is the formula given. Okay, in this formula, see, there are two terms, first term and second term. In what you observe in first term is, see, this is AP. Okay, AP. This is pi DLS. AP is the base area, pi DLS is skin area, right? Pi DL, the cylindrical surface area. Both of them are getting multiplied by what? QC. Okay, remaining terms are NJ, ND, and here alpha beta. So two additional terms are getting multiplied. In base capacity calculation, we are multiplying by NJ and ND. In skin friction capacity, we are multiplying by alpha and beta. So see, QS is the safe load carrying capacity of the pile in tons. So this is in tons. And this QC is also in ton per meter square. So units are same. If it is kilonewton, that is also kilonewton. Depth factor, ND, which is coming in base resistance. ND is depth factor 0.8 plus 0.2 LSD. So this depth factor is never greater than 2. It is always less than 2. Okay, so LS is nothing but that socketing length, which is also coming in terms of ND, like 4D, 5D. So if you use LS is equal to 5D, say 6D. So 6D means 0.2 into 6 is 1.2. So 1.2 plus 8 is 2. So maximum you can use is 60. Not more than that. Even if you are using more than that, ND will not increase. ND will be 2. Even if you are socketing up to say 8D, you can do that. But ND you will use only 60. Area of the pile toe. AP is equal to area of the pile toe. Pi d square by 4, we already know that. D is the diameter of the pile. LS is the socket length in the rock. Alpha is a rock socket slide resistance. Alpha and beta we get from the figures. We'll just see. Nj is the value as per the figure 2 of IS 12070. IS 12070 there is a figure. In that figure we get the Nj values. So this is the spacing of this discontinuities. So what is the spacing of the discontinuities? It gives us some Nj values. So from IS 12070 we can obtain the Nj values, and this alpha and beta. These alpha and beta are coming from the figure. See, this is alpha. Based on the QC values. QC values will come from the point load resistance, right? This is the uniaxial compressive strength of the rock. This is coming from the lab test. In the geotechnical report you will get this value, QC value. So this QC value is coming here. So for a given QC value, say this value, you come to the graph and you get the alpha value. This is alpha. Now similarly, this is a beta value. This beta value is dependent upon ED upon EI. ED upon EI is ED is discontinuities, I is intact. So your this is a EIXG. Actually, what is this now? See, you have a rock mass which is discontinuous, which has some cracks. So these cracks with the modulus of elasticity of this rock material with these cracks upon modulus of elasticity of the material where there is no crack, intact. So that ratio is called mass reduction factor. So this ratio gives us beta value. So if you don't have this value, for some reason your report is not complete, your technical report, you don't have this value, what we can do is we can take the least value, 0.4. Okay, this value we can assume for this calculation, and you refer beta as 0.4 and you start the calculation. If your report is quoting some value, use that value, and then from that, say your report is saying 0.6, you go to the graph and get this value. So that's all we can do. Now this is the based on pressure meter test. See, mostly we do with the UC value only, QC value only. Now if it is based on the pressure meter test, we can follow this formula, and some terms are defined here, and KB value is being used in the formula above. Here KB is used here. So based on that we get the KB value based on the socket length. So some calculations are given. This is very simple and easy to follow. We can refer that. Now we'll directly come to the structural capacity. The pile shall have necessary structural strength to transmit loads imposed on it ultimately to the rock as per the 2911 part 1 section 2. This already we have covered. Settlement for the piles could be estimated from one of the following methods. So there is an elastic settlement, PL by AE, everybody knows. Delta is equal to PL by AE, and then we have immediate settlement. So immediate settlement comes from this formula. So P is the load on the pile, D diameter, mu is the Poisson's ratio of the rock, not the concrete, right? I is the influence factor. Value of the influence factor can be taken as specified in IS 8009 part 1. So value can be taken from there. EP is the base area of the pile, and ED is the modulus of deformation of the rock mass. Okay. Then we have now we'll directly come to the lateral load capacity. Lateral load capacity, for understanding this thing, we must refer IS 1893 part 1 section 2 2011. Sorry, not 1893, it is 2911. There we have already seen how to calculate the lateral load capacity in annexure C. From there only we can do that, and we can assume some depth of fixity, and then we can apply the moment based on, and from cantilever method we can evaluate the reinforcement. Pile passing through soil of considerable thickness, intermediate thickness. For calculating the capacity of the pile socketed in rock requires determination of the depth of fixity, lateral deflection and maximum moment. 3 different embedments of the pile in the rock are encountered and the design is made accordingly. Piles passing through the soil or considerable thickness, intermediate thickness of the soil or in rock, pile fully embedded in the rock. So here there's a figure. So here what they are saying is where you are fixing your this pile will determine your fixity, whether it is a partially fixed, completely fixed, or is a flexible. pile. So based on this, you go to your 2911 part 4, part 1 section 2, and there are equations, or there is a graph which will give you what is the depth of fixed you to assume. So uh, this is the this is the relationship. Okay. So LS is the length of the pile in the soil, and R is the relative stiffness factor as per IS 2911. Okay. So this actually you have to evaluate. It is, I think, power 1 by 5 of some E value is to be used, and I think something is there, some formula is there in 2911 that we can take to calculate the R value, and LS by R we have to evaluate, and if it is less than 4, in case of intermediate, C, when the rock into which the pile penetrates is covered by a relatively thick layer of soil, the influence of the rock is negligible, and the method of estimating for capacity can be done similar to the method I mentioned in 2911. So what they are saying, if it is for case A, see, if rock is well below the soil layer is of considerable thickness, then we don't say that the rock is governing the design. We design as if the pile is embedded into the soil only, and we calculate the capacity of the piles as if they are embedded into the soil. And for intermediate pile, the end restraint conditions of the socketed pile should be accounted for in the estimation of the lateral capacity, that is the contribution of the rock can also be accounted for, taking into account the variation in the modulus of subgrade reaction with depth. When the pile is fully embedded in the rock, as shown in the figure 5c, with a higher modulus than that of the pile material, the lateral capacity it can resist is determined by the capacity of its section to resist the shear forces. So if you're in case of your pile is directly in contact with the rock, which rarely happens, and the rock is very strong than the pile, then whatever is the lateral capacity of your cross section of the pile to resist the lateral loads, like a cantilever beam. Suppose your pile is like this, your load is coming this, and your rock, this is your rock. So whatever this section, cross section of the pile can take along with this concrete and reinforcement, the lateral load, that is your capacity of the pile. For this we can refer, for this case, intermediate case, we have to refer IS 2911 part 1 section 4, lateral load capacity, and extra C. Uplift capacity is nothing but you have to remove the end bearing resistance, the skin friction plus the weight of the pile is the uplift capacity. Now these are some factors affecting the load capacity and the settlement of the socketed pile. Some factors are to be considered. Geometry of the socket length. See, why this factor is being calculated. This is being calculated to understand that whatever calculation you are doing based on the formula given here, this may differ case to case. Means it is not possible to exactly determine the capacity of the piles in the rocks. It will always depend upon the site conditions and some other factors from which you are evaluate how your site is different than the other site, and what are those factors. So these are those factors. Geometry of the socket defined by the length to diameter ratio. Modulus of deformation of the rock mass both around the socket and below the face. Strength of the rock in the walls of the socket and below the pile. Condition of the side walls with respect to the roughness and the presence of drill cuttings or ventures. Everything is very simple to read. You can actually read. Condition of the end of the pile and respect to the removal of drill cuttings and other loose material from the bottom of the socket. Means somebody is removing the drill cuttings completely, washing the hole clearly, and then doing concreting, and there is another person who is not clearing it completely. The contractor is not working properly, and he is just speeding up the work and not maintaining a quality. Then your end bearing resistance will be less. So then you cannot say that your end bearing resistance should be same for all the piles and for all the locations. It depends on how accurately you are doing your work, and piling is a completely blind operations, and we should be very careful. Like we should be doing whatever is given in the codes, and we should be following the codes properly. Otherwise the quality control will be very, very difficult. Condition of the end of the piles with respect to the removal of drill cuttings, layering in the rocks and the response of the seams with differing strength and moduli. So if your rocks has different layers within this socketing length, then and their modulus of elasticity will be definitely different, because E value is proportional to the strength. So if your strength is less, E will be less, and then its a holding capacity, the socketing capacity will be different. So there is this relative difference will lead to relative strains. So there will be some capacity difference in two different piles where this kind of situation is happening, and at some other location where only one type of E is there. Settlement of the pile in relation to the elastic limit of the side wall shear strength. So your settlement, if it is more than the side wall shear strength, then there will be some plastic deformation. If it is not, then there is no problem mostly. Creep of the material effect to the groundwater table. Spacing of the piles, you can read part 1 section 2 of 2911. Pile grouping, also same. Pile cap design. Factor of safety recommended for the rocks is 6. Okay. The factor of safety may be increased in case of unfavorable conditions of rock. If you are not sure about the rock conditions and you feel that the rock is not good, you can increase the factor of safety. So load test. So there are two types of load test in broad category. One is initial load test, which is performed on the piles which are not working piles, means they are not used in the structure. They are separately casted and then tested up to failure. Then we have routine test. In routine test, the piles are loaded to a slightly lesser load, and these routine test piles can be used in the structures. All the initial load tests are done up to 2.5 times of the estimated capacity, safe capacity. So this estimated safe capacity can be vertical, it can be lateral, it can be pull out, means uplift. So everywhere you are doing up to 2.5 times the capacity. So if vertical load capacity is say 1000 kilonewton, so you will test up to 2.5 times 1000, means 2500 kilonewton you will apply the load. If a lateral load capacity is say 50 kilonewton, then you will load up to 50 into 2.5, means 125 kilonewton. So you will apply lateral load, horizontal load up to 125 kilonewton, and you will start measuring the deformations. If it is pull out load is say 600 kilonewton, so you will apply the pull out load up to 600 into 2.5, means 1500 kilonewton. Okay, like that you have to apply. Then for vertical load, when you are starting to apply this vertical load up to 2500 kilonewton, you will plot the graph and you will see where you are getting 12 mm settlement. So wherever you are getting that 12 mm settlement, so your load displacement graph something, it will look like this. This is P, this is delta. So your graph is like this. Okay. So say for 12 mm, here it is 12 mm. For this 12 mm you are getting this value, this. So this value, so this is P1. So P1 into 50% of the load at 12 mm settlement. So this is 12 mm, this is P. So you take P1 by 2. P1 by 2 will be your safe load. Okay, this is how we obtain 1/3 of the ultimate failure load. What is happening is, you have like this, and your 12 mm is much below, but your 2500 is reached. Okay, so you are not able to reach 12 mm. So what you will do is 2500 kilonewton by 3 will be your capacity, safe load capacity. Okay, so routine test is carried out for a load test load of at least 1/3, 1.5 times the working load. So your capacity is say 1000 kilonewton, estimated capacity. So you will test up to 1500 kilonewton. And settlement of test loading in position shall not exceed 8 mm. For 1.5 times the load, your settlement should not exceed by 8 mm. This is the routine test. For lateral load, the settlement is 8 mm and 4 mm. You apply the, see, for initial, same, You have to test it to 2.5 times, 2.5 times. Embedded in rock, the safe lateral load is 50% the final load at which the total displacement increases to 8 mm. So in case of lateral load, we say displacement. For vertical load, we say settlement. So for vertical load test, we say 12 mm settlement, but for lateral load, we say 8 mm. 50% final load at which 8 mm settlement is observed, or we say, as we say in vertical load test, that ultimate load by 3, but here we say the final load is where settlement is 4 mm. One and a half times the working load, and settlement should not exceed 4 mm. Okay, that's very simple. So pull out is also same, 50% load at which the total displacement is 12 mm, or 40% of the load at which the displacement is showing a clear break, means the pile has been completely lifted. So if that is happening below 2.5 times the safe load, then you have to take 40% of that. Okay, this is called pull out load test. So this is it. Thank you for staying with me, and if you like the content, and if you like more reviews of such IS codes or any other codes that we are using in India, and referring to like in BS codes, ASCE codes, American Society of Civil Engineers, British Standard codes, or some other codes, then kindly comment in the comment box. I'll try to review them, and if there is any particular paragraph that you want to see, not the complete code, that also you can review. I'll make a short video on that paragraph. And thank you so much, and kindly support and subscribe if you like the content. Thank you.